Alright, Unit 3 practice exam for exponentials and logarithms. And we've got some inverse functions here for question 1. Part A, state, domain, and range. We can see along the x-axis here that that graph begins at -4 and heads off in that direction. So that'd be in the direction of infinity, so domain is -4 to infinity. Range along the y-axis starts there at 3. So we're going to say that the range is from 3 to infinity. Now part B says to graph the inverse. The way to find the inverse of a function is to switch the place of x and y. You can see the graph provided has some points marked on there. So for f of x, the xy points, we have -4, 3, we have -3, 4, and we have 0, 5. Those are those 3 points that are marked on f of x. If we were to find the inverse, we simply switch the place of x and y. And that gives us 3 points we can graph: 3, -4, 4, -3, and 5, 0. That gives us 3 points we can graph for the inverse. And then it wants us to state the domain and range. So we can see on the inverse here, so I'm going to mark this as inverse. On the x-axis, the first point in the domain is 3. We could also see from part A that the domain represents our x values and the range represents our y values. So for the inverse, those are going to be switched because you switch the place of x and y. So the domain for the inverse is 3 to infinity, and the range for the inverse is -4 to infinity. Now for question 2, find the inverse. Again, the way to find the inverse is switch the place of x and y, and then solve for y. And remember, you can think of f of x as y, so the first step would be to switch the place. And then we need to solve for y. So we don't want to really have a fraction here in our equation, so I'm going to multiply both sides by the denominator. And then I'm also going to go ahead and distribute that x. So I've got xy minus 4x equals 3y plus 1. Now I've got a y here and a y there. I don't want to have y's on opposite sides of the equation. So I'm going to need to get the y's on the same side. So I'm going to subtract the 3y here and add the 4x here. So now my equation becomes xy minus 3y equals 4x plus 1. Now that both of those terms have a y, I can factor it out. And then divide by x minus 3. And then that's the inverse. All right, question 3 is from section 4.2, graphing exponential functions. you'll recall that a typical exponential function with no transformations has a horizontal asymptote right there on the x-axis, a y-intercept at 0, 1, and if it's a growth function would look like that, or if it's a decay function would look like that. That's if there's no transformations. Now, what we have here is a transformation, that -1 right there, that moves the graph down 1 unit, including the horizontal asymptote. So I'm going to place the horizontal asymptote at -1. And then we need to find the y-intercept, and we find the y-intercept by letting x equal 0. If you plug a 0 in for x right there, you're going to have 3 to the 0, which is 1. 1 minus 1 is 0. So the y-intercept is at 0. And then you just need 2 more points. So I'm going to plug in x equals 1 and x equals 2. If x equals 1, you get 3 to the first power, which is 3. 3 minus 1 is 2. And then if x equals 2 right here, 3 squared is 9, 9 minus 1 is 8, so 2, 8. So the domain of any exponential function, if you'll recall, is negative infinity to infinity. Range, we can see here that this graph goes down as far as -1. Doesn't actually hit -1, so I'm going to use parentheses, -1, and it goes up as high as infinity. Also wants an equation of the horizontal asymptote. This horizontal asymptote has the equation y equals -1. Okay, question 4 is from section 4.3, graphing a logarithmic function. Now, you're going to want to recall that typical logarithm functions have a vertical asymptote at x equals 0 and an x-intercept right there at 1, 0. That's if there's no transformations. But here we have moving to the right 2 units and moving up 1 unit. So that's going to move our vertical asymptote and our point right there. So first of all, the vertical asymptote, because of moving right 2 units right there, the vertical asymptote moves right 2 units. And then remember this point that I had marked at 1, 0, that's going to move over 2 units. So 1, 2, and then move up. So we know there's a point right there. Now we want to make a collection of points here. And since we have a log base 3, I want to choose values of x so that when I plug them in, I get a number inside that parenthesis that's a power of 3, like 3 or 9 or 27. So if I plug in a 5, for example, if I plug in a 5 for x, 5 minus 2 is 3, log base 3 of 3 is 1, and then 1 plus that, 1 there, is 2. So I know 5, 2. 1, 2, 3, 4, 5. I know 5, 2 is a point on my graph. I'm also going to want to plug in 11, because if I plug in 11 for x, 11 minus 2 is 9. And 9 is 3 squared, so log base 3 of 3 squared, the 3's cancel, I'm left with a 2. So log base 3 of 9 is 2, and then 2 plus that 1 is 3. So now 11, 3 is on my graph. So as you recall, when a graph nears a vertical asymptote, it doesn't just stop, it scoots along it like that. So the domain is parenthesis 2 to infinity. The range is negative infinity to infinity. And the equation of the vertical asymptote is x equals 2. Okay. Part A, B, and C here are meant to be done without a calculator. And then part D, use change of base, that's meant to be done with a calculator. So part A is pretty simple, 1 natural log, and E are inverse operations, so they cancel each other out, leaving a 3. Part B is easy to do as long as you know, it's not a trick, but know what to do, I suppose, with that negative 2. And here's what I mean. If we had 7 and then log base 7 of just plain 3, then we would know that the 7 and log base 7 cancel. However, we've got this negative 2 right here. So let me go ahead and erase this 7. If it was just negative 2 log base 7 of 3, then you might recall from 4.4, if you have a coefficient of a logarithm, you can always move that coefficient up as a power. So it becomes 3 to the negative 2. So that's what needs to happen here, is this negative 2 needs to move up as an exponent, so we can write this as 7 to the log base 7 of 3 to the negative 2. Now the 7 and log base 7 cancel, leaving 3 to the negative 2, which is 1/9. Now for part C, if we had log base 2 of 2 to some power, then the log base 2 and the 2 would cancel. So that's what we need to do, or try to do, for part C. And remember that logarithms and radicals, so that square root sign, it's not a good mix. So I'm going to write this as log base 2 of 8 to the 1/2. And then I'm going to change 8 to 2 to the 3rd power. And then if you have a power raised to a power here, remember powers multiply. So then we could write this as log base 2 of 2 to the 3/2. Now the log base 2 cancel, leaving 3/2. Now for part D, this is log base 4 of 19. Change of base tells us that this is equal to common log, so log base 10 of 19 over log base 10 of 4. That's something we would do in a calculator. So log, let's see, log 19 divided by log 4 is 2.12. Now, question 6 is from section 4.4, properties of logarithms. We're expanding, and since we have a product there, you can expand the product with 2 separate logarithms that are adding. So log base b x to the 3rd plus log base b of y to the 5th, and then we move the exponents in front as coefficients. So 3 times log base b of x plus 5 times the log base b of y. Now for part B, we have a quotient, so you can expand a quotient using separate logarithms that are subtracting. So the numerator minus log base b as the denominator. Now we have a product right here, so you can expand that. And because we're subtracting an expansion, this has to be done in a parenthesis. So log base b of y plus log base b of z cubed. Now I'm going to distribute that minus sign. So log base b of x minus log base b of y minus, I'm also going to move that 3 down in front. All right, that is 3 times log base b of z. Okay, for number 7, compounded continuously means we're going to use that formula where A is the future amount, P is the principal investment, which is $12,000. That's our interest rate, 0.05. How long will it take means we're trying to solve for t. What does t equal? So I need to know a future amount, and it's going to double. The future amount means it's going to be 24,000. The principal investment was 12,000. We have to solve for t. Now, t is an exponent. We can't solve for variables if they're exponents. It means we got to cancel a base. So I need to isolate this term here before I can cancel that base e. So divide by the 12,000. Now to cancel the base e, I need a natural log, but I got to do it on the other side too. So natural log of 2, and then divide. So t in years, natural log of 2 divided by 0.05. So natural log of 2 divided by 0.05 is 13.86 years. Okay. Number 8, these are from section 4.5, solving exponential and logarithmic equations. And it wants the exact and approximate solutions. Exact means you leave your answer in the form of a logarithm. Approximate means you type it into a calculator, get a decimal. So we're solving for x. It's an exponent, which means we're going to have to cancel a base. But I can't cancel that base using a logarithm until that's the only term on that side of the equation. So I've got to isolate it by subtracting 5. Now I can cancel that base using a log base 2. So I've got log base 2 of 22 equals 3x minus 1. Now I'm going to add 1. And then divide by 3. So the exact answer, log base 2, 22 plus 1 divided by 3. So that's the exact answer. The approximate solution I'm going to have to type into a calculator. Remember though, don't have log base 2, so I'm going to have to use change of base. So I'm going to call this log 22 over log 2 plus 1 all over 3. That's what I would type into a calculator. This is my exact solution. So Come back here, let's try this. Log 22 divided by log 2. Then I'm going to add 1. Then I'm going to divide by 3. I get 1.82. All right, for part B, I need to get this term here by itself before using a natural log. So I've got to subtract the 9. Then divide by -2. Now we can use natural log to cancel the base e. And I have 0.1x equals natural log 4 divided by 0.1. So x equals natural log of 4 divided by 0.1. That's my exact form of the solution. Now the approximate is going to be on a calculator. Natural log of 4 divided by 0.1. That's 13.86. Okay, part C is a very particular kind of exponential equation that we saw in 4.5. It is exponential, that's going to require logarithms, but it's also quadratic in form. What I mean is e to the 2x is the same as e to the x squared. So I'm going to write this as e to the x squared minus 4 times e to the x minus 5. And then rather than e to the x, I'm going to substitute with a different variable u. So I'm going to say e to the x, I'm going to call that u. Now we have a quadratic equation to solve by factoring. So we have u equals 5 and u equals -1. Remember though that u is e to the x, so e to the x equals 5 and e to the x equals -1. Now we need to solve for x on both of these equations. Over here I'm going to use natural log, and we get x equals natural log of 5. Over here, if we try to use natural log, you can't take the natural log of -1. So that one gives us no solution. So over here we get x equals natural log of 5. That's the exact form. Natural log of 5 is 1.61. So that's the exact and approximate form of both of those. Question 9 is still from 4.5, solving logarithmic equations now. To solve a logarithmic equation is going to involve canceling a logarithm. A logarithm is canceled using a base. Now, since we only have a single logarithm here, we can go ahead and cancel it using, in this case, a base of 3. So base of 3 cancels log base 3. So we have 2x minus 1 equals 3 to the 4th, which is 81. Add 1, get 2x equals 82, divide by 2, and we get x equals 41. For part B, we have multiple logarithms on the same side of an equation. You can't solve a logarithmic equation if you have multiple logarithms, so we've got to condense those into a single logarithm, and since there's a plus sign there, we condense using multiplication. So x minus 3 is going to multiply with x plus 2. And now that we have one logarithm on one side and one logarithm on the other, we can go ahead and cancel both, since they're both base 10 logarithms using a base 10. So those cancel, and we have that, which I'm going to multiply together to be x squared minus x minus 6 equals 4x. So now we have a quadratic equation to solve. Remember, quadratic equations are most often solved by getting one side equal to 0. So I'm going to subtract and then that's going to factor. We get x equals 6 and x equals -1. Now, if I tried to plug in a -1 there, for example, 4 times -1 is -4. Can't take logarithm of negative values, so x equals -1 is not a solution. That was called extraneous. Still, I might want to check 6. If I plug in a 6 there, it's okay. 6 plus 2 is 8, that's fine. 6 minus 3 is 3, that's fine. So x equals 6 works out okay. For part C, again, we have multiple logarithms there. So that's got to be condensed. And since there's subtract, those are going to be condensed using the quotient property. So 2x minus 5 divided by x minus 3. Now we can get rid of the logarithm, in this case using a base 10, because it's a base 10 logarithm. So that cancels. We have 2x minus 5 divided by x minus 3 equals 10. Now, I don't want to have an equation with a fraction in it, so I'm going to multiply by the denominator. Now I've got 2x minus 5. I'm going to go ahead and distribute there. Get 10x minus 30. And I'm just going to solve the equation. We get 25 equals 8x. X equals 25 divided by 8. And now number 10 is from 4.6. This was applications of exponentials and logarithms. So we have an equation here that gives the population of trout. T is a time in years. How long will it take? So how long will it take is a question of time. T equals for the population. So the population is going to be, how long will it take for the population to be 5,000? So this value needs to go in place of P of T right there. So 5,000 equals 10,000. And that's the equation we need to solve. So again, I'm not liking this equation with a fraction in it, so I'm going to multiply. That's going to cancel it there, and I'm also going to multiply here. So now rather than distributing, I could distribute, but another way to get rid of that 5,000 is to just divide by it. It's going to make things easier. And then I can subtract 1. divide by 19. And now I can solve for t. Since it's an exponent, I need to cancel the base. And since it's base e, I'm going to use natural log. So I've got negative 1.56 equals natural log 1/19. Oops, negative 1.56 t, there we go. And then I can divide by negative 1.56. So t equals natural log of 1/19 divided by negative 1.56. So natural log of 1/19 divided by negative 1.56. 1.89 years.